In this lesson, we'll discuss one of the important experiments that ushered in the quantum view of nature at the submicroscopic level, the double-slit experiment. We'll see that electrons, like light, can undergo diffraction and interference. Let's start with monochromatic light diffracting and interfering as it passes through a pair of closely spaced thin slits. The interference pattern produced is clearly characteristic of waves. Suppose we dim our light source, allowing an effect that only one photon at a time reaches the barrier with the thin slits. If a detecting screen behind the barrier is exposed to the light for a very short time, its exposure shows only a few grains. Each spot on the screen represents exposure by a single photon. If the exposure is for a longer time, a pattern of fringes begins to emerge, as we see here. This is quite amazing. Spots on the detecting surface are seen to progress photon by photon to form the same interference pattern characterized by waves. If we cover one slit so that the photon striking the screen can pass only through a single slit, the tiny spots on the screen accumulate to form this single slit spread out diffraction pattern. We find that photons strike the screen at places they would not strike if both slits were open. Thinking classically, we ask how photons passing through the single slit know that the other slit is covered and therefore fan out to produce the wide single slit diffraction pattern. Or, if both slits are open, how do photons traveling through one slit know that the other slit is open and avoid certain regions, proceeding only to areas that will ultimately fill to form the fringed double slit interference pattern? The modern answer is that each single photon has wave properties as well as particle properties. A photon behaves as a particle when it's being emitted by an atom or absorbed by a photodetector, and behaves as a wave in traveling from a source to the place where it is detected. So the photon strikes the film as a particle but travels to its position as a wave that interferes constructively. The fact that light exhibits both wave and particle properties was one of the interesting surprises of the early 20th century. But there's a bigger surprise. Objects with mass, such as electrons, also exhibit a dual wave-particle behavior. When a beam of electrons is substituted for a light source, the pattern produced is much the same as the pattern for light. We find that both light and a beam of electrons travel in a wave-like way. The fringes at the left are produced by the diffraction of light passing not through a slit, but passing the edge of a barrier. The fringes at the right are produced by the diffraction of an electron beam. Amazing! In 1924, a French graduate student, Louis Dabrogui, submitted his doctoral thesis that did more than assure him a PhD in physics. It later earned him a Nobel Prize in physics. According to Dabrogui, every particle of matter is somehow endowed with a wave to guide it as it travels. Under the proper conditions, then, every particle will produce an interference or diffraction pattern. Each body, whether an electron, proton, atom, a mouse, you, a planet, a star, has a wavelength that is related to its momentum by this equation. Wavelength equals Planck's constant divided by momentum. Here we see h is Planck's constant. A body of large mass and ordinary speed has such a small wavelength that interference and diffraction are negligible. Rifle bullets, for example, fly straight and do not pepper their targets far and wide with detectable interference patches. Let's calculate the wavelength of a bullet of mass 0.02 kilograms traveling at 330 meters per second. We get plugging in the appropriate values, (10⁻34 meter. I'll leave it to you to show that the units indeed convert to meters. We see that 10 to the minus 34th meters is an incredibly small size, a millionth the size of a hydrogen atom. An electron traveling at 2% the speed of light, on the other hand, substituting in the denominator the mass of an electron and its speed, has a wavelength 10 to the minus 10 meters, which is equal to the diameter of the hydrogen atom. Diffraction effects for electrons are measurable, whereas diffraction effects for bullets are not. Diffraction of particles as small as electrons and protons can be appreciable. The world of the quantum is an exhilarating one. I want to leave you with a question. We don't notice the de Broglie wavelength of a pitched baseball. Is this because the wavelength is very large or very small? Let de Broglie's equation guide your thinking. Until next time, good energy.